We're given that A represents a transformation T, which is a reflection in a certain straight line. And we're also given that this straight line, the mirror line, passes through the origin. Find why there must be a line of invariant points for T to state the geometric significance. So an invariant point is when you apply a transformation and the point stays exactly where it is. And the line of invariant points is like a whole line of these points that stay exactly where they are. And the first thing I thought about when doing this question is, let's say reflecting a shape like this, then of course, they don't stay in the same place. But if you ever have a point on the mirror line, then it is going to. And that's what this question is really all about. So I said any point on the mirror line will reflect to the same position. And hence will be invariant. And state the geometric significance. Therefore, the line of invariant points is the mirror line itself. By considering the line of invariant points for t, determine the equation of the mirror line. Give your answer in the form y equals mx plus c. So what we have to do here is find the line of invariant points, and then we've got our answer for the mirror line, as we said in part A. Therefore, I can apply 1 over 13 times 5, 12, 12 minus 5 to a general position vector, essentially a coordinate x, y. And that is going to equal the same thing because that's what it means to be invariant. It goes back to the same position. I'm going to multiply out the matrix. So I'll get 5x plus 12y and 12x minus 5y equal to xy. So this means that 5x plus 12y is going to equal 13x if I times through by 13. Therefore, 12y equals 8x. Y is 8 over 12, or 2/3 x. Just need to check that the other one is consistent. So 12x minus 5y is equal to 13y. 12x is 18y. Y is 12 over 18x. Y is again 2/3 x. So y equals 2/3 x for both. This is the line of invariant points, and hence the mirror line. Coordinates of the point P are 1, 5. By considering the image of P under the transformation T or otherwise, determine the coordinates of the point on the mirror line which is closest to P. So this might take a little bit of time to understand what it's saying, but essentially we've got some point, and we know that T is a reflection, so it's going to take us to here. Well, let's apply the transformation to see where we end up, what the image is. In fact, we've kind of already done the multiplication, but I think I'll just do it again. So I'm going to get 1 over 13, and it's 5 plus 60, so 65. And then 12 minus 25 gives me minus 13, which takes me to 5 minus 1. That is going to be my image. So determine the coordinates of the point on the mirror line which is closest to P. Well, we know we can connect these at a right angle, and that's going to give me the point that's closest because the straightest path is going to be at a right angle rather than sort of down here. And hence it's going to be the midpoint. So point closest to P on the mirror line will be midpoint. I could just add the two values together. 6 divided by 2, 3. That's halfway between 1 and 5. And then 2, halfway between 5 and -1. It's this point here. Finally, the line with equation y equals ax plus 2 is an invariant line for t. Determine the value of a. Okay, this is slightly different. So an invariant, a line of invariant points are where they actually always map back to themselves. Whereas an invariant line means when you apply the transformation, it stays on the line somewhere. Like it might move to a different position, but it's still on the same line. And this question can be answered really quickly. You don't have to do all the equations for an invariant line, although I will do them afterwards. But with a reflection, if you basically take any line that's perpendicular to the mirror line, then you're always going to end up on it. So this point would move down to here. We're not gonna move off of the line. So we just need to find the gradient that's perpendicular to the mirror line, and we know the mirror line is y equals 2/3 x. So in fact, it's got to be the negative reciprocal -3/2. And that is our answer straight away. So since, I was about to say line of invariant points again. So since invariant line will be perpendicular to the mirror line. Let's just go through the process of deriving it algebraically, like a worthy thing to try, because it's easy for me. It's easy to forget, I think. So we've got 1/13, 5, 12, 12 minus 5. And we're looking for a line in this form. So I've got my x value and then my y value, but I know my y value is going to be ax plus 2. And I'm looking for a new x value, but then it's going to equal this new x value times a plus 2. Then it will still be on that same line. This is the equation I've got to try and deal with now. So again, I'm going to multiply out the matrix. Of course, you can see, you don't want to do it like this. You want to do it just that quickly, but it's worth practicing, just like I said. So 5x plus 12ax plus 24, and then 12x minus 5ax minus 10. So we can say that 5x plus 12ax plus 24 is equal to 13x dash. And also that 12x minus 5ax minus 10, 13a x dash plus 26. So now I can sub in, I've got my 13x dash, I can put it in here, replace it by 5x plus 12ax plus 24. Which will give me 5 ax plus 12 a squared x plus 24a plus 26. And I'm going to look at the coefficients of x to the 0. So on the left-hand side, I've got minus 10. On the right-hand side, I've got 24a plus 26. Therefore, 24a is equal to minus 36. A is equal to minus 36 over 24, which is minus 3 over 2. I guess we should probably check that the rest is consistent. I mean, although we have been told that it is an invariant line, so you could argue that is enough. Anyway, that's just a little reminder of how you can deal with invariant lines. Good question. Well done.